Okay, recording. Why? Huh? Okay. Hello, everyone. Thank you, and Dr. Eric, and thank you, Center Faculty Scholarship Award. This grant for us, for me, and my students, Joshua, Laurie. So today we report it to you, and we hope you enjoy it. And thank you again. Now, and Josh, are you ready? So
Yep.
we can
Here.
present it now for the Dr. Eric and also for CFS. Okay, thank you.
Perfect.
Okay.
All right. I'm going to start my slideshow now. So yeah, like Dr. You introduced Josh Lorraine, and this was my project for the grant, which obviously we're still very thankful for. It was an environmental monitor system with visual analysis. Yeah, some of the curriculum that it touched upon, AUC number 29, the engineering technologies 3900 device interface design. AUC 36, the engineering 4903, engineering technology capstone. AUC 38, the engineering technology 4110, microprocessor slash controller and embedded systems. Yeah, so a little background on the project in general. Engineers incorporate sensors into a variety of consumer products such as security cameras, remote control devices, night vision equipment, chemical analysis instruments, as well as many other technologies that collects data about the universe around us. Very important nowadays, especially. Sensors eventually found their way into civilian markets due to the development of integrated signal readouts, thanks to better silicone technologies. It's always evolving and developing. This allowed for much more commercial use of these sensors. The sensors collect data for server artificial intelligence, machine learning, deep learning, UAVs, unmanned vehicles. Another large step was the development of FPA arrays by integration with charge-coupled devices, and this breakthrough allowed the development of high-performance sensor systems of smaller sizes, lightweight, and lower costs, so more efficient in general. The objective of my project was to create a functioning system of sensors, each recording different readings in which the results are visually represented and analyzed. The project would utilize hardware, software, and embedded systems with potential for a lot more. Utilizing this system, the user can monitor temperature, humidity, and CO2 levels wherever the hardware and the sensors were placed. LEDs would also be attached to the system, giving a physical indication of preferred set limits to the readings. And these factors were considered when going about this project. Number one, it's a little rubric. Number one, project must utilize sensors, microcontrollers, and visual analytics. Two, project will be fully functional. Three, the project will be efficient in terms of cost and function. And four, completed project will be user friendly to operate. Little flow chart of it. It starts out at the hardware, which some listed sensors that we were hoping to use were temperature sensors, an IR sensor, MLX 906. Another one, humidity detection, AM 2302, and then possibly, if need be, which turned out we did need be, another temperature sensor, TMP 36. And then it gets down to the embedded systems, and for that we interface devices, and we use it's the microcontroller microprocessor. This was attached to the Arduino Uno board that we were using. And then into the interface, it's the software. It's on your PC, and we're using LabVIEW. And LabVIEW, the coding in LabVIEW is it's graphic language code. It's G code, but there's a couple G codes out there, and it's not the one for the automation. It's another G code. But yeah, and then We have the possibility of using a MySQL database. Like I said here on the side, I would be able to construct everything except for the MySQL. I haven't had any use with that, but the potential for its use is there, and it's essentially just a database, so it can store and keep information, for later usage. Yeah, and it would. This was intended to be a future feature that would hold great importance in practical applications. Yeah, like I said, the MySQL would be able to store the info gathered from the sensors and software, allowing it to be analyzed at later dates. All right, basic little how it works. The hardware it's a circuit of sensors, resistors, diodes, and capacitors. It would be physically attached to a breadboard. This board would be attached to the embedded system using an Arduino Uno unit, and then get to embedded system using PIC microprocessor slash controller technology. We use Arduino Uno as a platform. The system will be the brains of the operation, communicating between the physical components and the PC software. And then it gets us to software. The LabVIEW utilizes G code, as I said before, to give the microcontroller instructions. LabVIEW also collects and converts the data from the Arduino to be visually analyzed by the user. So it'll be, very user friendly. Schedule this was kind of a final schedule. So, purchase and install LabVIEW that lasted from in just January. Then developing LabVIEW skills that started in January and went to February, but really it extends the whole time. Every day I use LabVIEW, I get better at it. So, but that was just strictly for like other projects and such. Simulate a model and hardware interaction. That was March. Just took about most of March. The implementing of the sensor projects in practice. That that was probably the most stretch of time. So going from March into May, and the packet report and presentation, which basically where we're at now. Just yeah, this month May. Budget. So we got one of the temperature sensors. It's about $5. So a couple of those, and it's roughly $10. Humidity detection, that's a little bit more expensive. And again, you're gonna want a couple of those in case one, malfunctions or whatever the case might be. So, and that'll be about $16. The Arduino Uno control board, only really need one of those, and they're $25. The LabVIEW student, $30. It's just it's a limited basis. Really, you have it as long as you're a student. LabVIEW, when you're not a student, it can be thousands of dollars. And then my PC that I use is a Asus laptop with Windows 10. It's about $1,400. And yeah, and then the engineering salary, at least $35 an hour, and I've done 40 plus hours worth of work. So yeah, that adds up. All right, and then this was the ideal software interface. So this was the front panel in LabVIEW, and this was what the user would be looking at, and it would all be running. We have the sliders are in it. You set those sliders for the LEDs. Those are the limits I had mentioned. And then yeah, when say a temperature falls in between one of the your sliders, that's kind of where you want it to stay. And then say if it rises above what you set a slider at, then the LED will kick on, indicating that hey, this is above or below the temperature that you wanted, or the humidity, or the carbon dioxide levels. This was the code for it. Yeah, so LabVIEW doesn't really utilize. It's not like C++ or Java even, where you type in like words and such. It's much more user friendly, and there's a bit of a learning curve, but yeah, it's I think it's easier to develop your skills with it. All right. Yeah, obviously we ran into some complications with the COVID-19 pandemic. It struck right in the middle of this project, causing the university and many businesses physical closure, which everyone's aware of. This hampered my ability to gain needed supplies and also hands-on guidance and troubleshooting help from both Dr. Yu and the university. We didn't have, I lost access to the labs and all the equipment and everything. So it was that took a big hit on us. Um, I became limited to only being used. I think last semester, Doctor U had given me one IR sensor, and it was a MLX 906. And so that means I had to that was the only sensor I had. So I had to redesign my project to be a single sensor system as opposed to the intended three sensor system that I was hoping to achieve with the three sensors being temperature, humidity, and CO2. But while utilizing this IR sensor, I could get it to operate within the system, and it was working. And it would appropriately react to temperature change. It could tell if, say, I held a lighter above it, the readings went up. It was acting appropriately, but it was giving me a wide range of readings. It wasn't static at all. It was constantly fluctuating. It was a we couldn't lock it in. So and a way to fix this was, say, a voltage regulator or introducing more capacitors and resistors. And from what after trying, I was troubleshooting it for a long time, and I couldn't get the right combination or anything to reduce its range. So it just wasn't accurate enough for what we were looking for. So I had to switch it out to the only other sensor I had. That was a TMP36 low voltage sensor, and that came with the Arduino packet there. And yeah, I ended up getting that one to work good. So this was the final one that came out to be. It's about a third of what the intended project was supposed to be. So yeah, some conclusions. This project had tremendous potential to evolve and become more useful and powerful, and it still does. Some applications can range from being a monitor system for a household, like the solar decathlon, how they're using it for their greenhouse. It could do a lot of things for that project. To being inside even an automobile or an aerial vehicle, anything. Microcontroller technology has it seems limitless possibilities right now. Um, yeah, I believe that even after suffering large drawbacks due to the ongoing pandemic, this project was and is a success. With further evolution of this project, the potential applications in civilian, military, and private sectors are very high. And that was the physical layout of it. Here I got a video of it working. Take you to. Let it load. Well, it might not load. I might have couple too many things going on my computer right now.
It's working.
Is it?
Yeah. Hold on 1 second because your buffer.
Okay. It wants to work. It's
Yeah.
not giving me much life. And if we can't get this video working right now, we just have we can I can the link can be incorporated, or we just reshoot just the video.
Yeah, you just play the video you recorded.
Mm.
Mm,
Yeah, looks like it keeps not wanting to work.
yeah. I think that's your laptop.
It might be my laptop. It's old.
Yeah.
Um, Not a problem. Like I said, we'll just do another shooting too, where we'll incorporate the video.
Yeah. You can
So
play it. You can play it on desktop.
yeah, there. Now it's everything's slowing up. Go back into the presentation. Slide through some. Perfect. Little reference sheet.
Okay.
Yeah, thank you guys for listening. Thank you for the project and the grant and all this. It's been a lot of fun and learning experience. Any questions?
So can you play the video on your desktop? I
I
think
can.
I think you recorded by your smartphone, right? Or
Yeah, I recorded it on my phone, and so I can. I'm not sure how you want me to go about it.
but you copied on the desktop?
I just I uploaded it to YouTube from my phone directly, so it's not
Oh, okay.
desktop.
Okay.
Um,
Can you use the form to log in?
yeah, to the video and like hold up the video to the camera, maybe.
Yes. Maybe from you because you just add one person, so we can see.
Let's see. It might not be the
Uh,
best quality though. Here,
yeah, we'll just try if can work. That's
we'll
great.
try. Let me know if it looks all right.
Yeah,
I'll go to my channel.
yeah. Go to log in.
Yep. All right. Can you are you seeing just my screen or are you seeing me as well?
I can see the screen.
All right, here.
You should add the one after add the screen. I give you permission to log in.
Sure. So you want me to turn the camera around? I could like hold up my phone video, or do you want me to? I'm still not sure 100% how you want me to go about it. You want me to?
Okay, okay. Try the video YouTube again.
All right.
Maybe it's working now. It's okay.
It wants to work, but I think there's just too much going on. It's not gonna work. Um. Yeah. Here, I can turn the camera around and have the camera facing me, and then I can just hold it up on my phone if you want that, or
Oh yes. You can do that way. It's
you want
okay.
to do
It's
that.
okay.
That's about
I
the only
just
thing I can think
I
of
just
right
yeah yeah. It's great.
here. I'll cancel out of that. All right. How do I turn this around here? Do I hit stop presenting? I think.
Yeah.
And it'll go to me.
Mm-hmm.
Cool. Can you see me?
Yeah. Good.
Yeah. Yeah. Here's my interface. Here's the hardware. We have a few LEDs, a couple resistors, a capacitor, and right here's a little temperature sensor. And yeah, we have a waveform chart here to represent the temperature coming in. You can see it's quite noisy. We can reduce this by adding a voltage regulator or more filters, and it's kind of the idea behind this first capacitor and resistor. You can continue to add more of those if you really want, but this does the job just fine. And yeah, so let's get into it. When the temperature sensor goes above, I got it set about 65 degrees, it will kick on one LED. And when it goes below 55 degrees, it will kick on another LED. So yeah, see it in action. Start. Just take a lighter here that I got. We will hold it near the temperature sensor. Be sure not to burn it or yourself. And you can see it start to rise. And boop, the indicator came on. Look at that. And that LED lit right up, as it says there. And then hold a big ice cube here. We're gonna hold it right up, touching the sensor. See how the temperature's already dropping. We'll monitor it here. See, it's flirting with 55 degrees, and as soon as it gets under,
Okay.
it's gonna hold.
Okay. I saw the LEDs on. Blink over there. Yep. Okay.
And it's gonna get steady though as the temperature drops. It's. And there we go. It's gonna continue to drop. I don't know what that is.
Oh, that's great. Yeah.
Take that off.
Yeah, I can see the high temperature. I can see low temperature LED indicator is on and off.
Yep. And yeah.
Okay.
On the physical, it's the other LED that lights up. You know, you have two of them. Soon here it will kick off, and
Okay,
then yeah. See, it's
that's
flat.
great.
Yep.
So can you present the first slides of the PowerPoint slide and go back?
Go back.
Yeah,
Yep.
first slide.
I got to hit present.
Yeah, so first slide.
Let's see. Let's see.
First, no, before. Okay,
You know,
okay. This one that's for every month the monitors the systems the virtual analysis, right? So
correct.
and we are get this grant award from 2020 CFS faculty student grant. Okay. So and also second slide, please go to second. So second slides the and also this grant to support the engineering technology department curriculum. So that's AUC number 29, 36, and 38. That's correct. So and that one is a device interface because this one included software and the hardware, and
Yep.
we see that. And the second for about the another one that's for capstone, and the third for microprocess. Microprocess they use the different language. So you use the graphic and
Yep.
the G language. So
Yep. A lot of other
so
controllers I know utilize either
yeah,
assembly language or even
yeah.
C.
That's great. That's great. So because we are engineering, so we should use the engineering program or language. So that's why you use the geographic, right?
Yep.
Okay, the G language. So and I have one questions for you. Okay, go to first slide. Go to first slide. So I have one question for ask you. So
Sure.
for we have a lot. Did you see that? I saw have a lot of noises. Still have a lot of noises. The
Yeah.
range or setup. So do you and you are graduate. You are senior graduate. You are have a
Correct.
electronics engineering and technology concentration. So my
Correct.
question is for all these noises, how to filter, how to get out all these noises.
Yeah, I kind of mentioned it in the presentation already, but there's like you said, you can add a voltage regulator. You can, but that's a physical component that I didn't have. You can also add in capacitors and resistors to try to slow down the current, limit the current, and yeah, we just couldn't get it. It was just the first sensor we used, the IR, the MLX 9016, I think it was. It was just way too sensitive, and we couldn't. I don't know. We didn't have the capabilities of slowing it down. Essentially, yeah. But
So we okay,
we
okay.
yeah, yeah. So
According you says that we can use the look like RLC and as a filter for the
yeah,
noise. And the second, you can use the regulator. And the
yeah,
third we can maybe use the software to do that. So
yeah,
that's you mentioned. That's three
yeah,
way we can kick out all these noises. But
yeah.
temperatures that we haven't, in these times the virus the penetrate. So and we have a lot of trouble to get in the lab. So if we have a more lab have opportunities, so we can design the filters to and kick out all
Yeah,
noise.
that was the big thing, was the lack of. I mean, obviously, there's much more pressing things happening than keeping the lab open. You know, it's a pandemic, so but that was a big drawback for us because, like I said, we couldn't physically I couldn't physically troubleshoot it with you or with
Uh,
all the equipment that the labs offer,
yeah,
and
yeah.
so yeah, it was everything. We're all doing it at home and over computers, so.
Okay, and the second question is the Josh. I will ask you.
Sure.
And for our elements, the monitor systems, with the virtual analysis.
Yep.
So what in future? What's supposed to apply the area? Application area.
Sure.
So for
Yeah, yeah. Like I said, it's kind of endless, really. I mean, every market could utilize this. from monitoring your house, if you want to have like a constant stream of like the solar decathlon project, where
Mhm.
it recognizes, hey, it's at a certain temperature, and then it kicks on the AC or it kicks on the heater,
Mhm.
um, just yeah, from simple ones to like that to say being on drones, where it uses the IR to pick up information. Yeah, it could
Yeah.
be in a factory even, if you gotta you hook it up to say some equipment that you have that you have to keep a constant eye on, make sure it's not overheating, and you get alerted if it hits a certain temperature or whatever, and temperature is just one of the many sensors that could be used, like we said, we're intending on using three of them, so from temperature to CO2 level monitors to humidity. There's a bunch more sensors you can add as well. So
Good.
the limits, it seems limitless right now, really.
Good. Very good. Very good. And the last one, I for you, not for you, for whole the project.
Sure.
So in futures, what do you think about challenges inside? You think maybe database or
Yeah,
yeah.
yeah. So that's possible. One possible kind of expansion of it. The database learning my SQL. That we had talks about there's other students here at the university that do know it, and I think we could have worked with other students too if we weren't, like I said, hampered by this whole pandemic thing. If we were able to work in person, I think we could have even used my SQL for this.
Mhm.
Um, but
So
yeah,
maybe this one is good for cooperate with the other department, look like computer science guys. Then maybe they
absolutely, absolutely, yeah,
yeah.
yep.
Look like your friend Prince.
Yep, yep. One of my good friends and roommates, Prince, he's a computer science major as well, and
Yeah.
I know he uses and he's familiar with
Uh,
MySQL. So
okay, that's great. So that means that in future, so we can cooperate with other, and
other
department,
departments,
and
yeah,
we can set up a new project, set up a database for whole the system. That's you mentioned, right?
yeah, absolutely. And I,
Okay.
I think that would be a really good idea because that, I mean, when
Yeah.
say you get into the professional level, that's what it is.
Exactly.
You need to be incorporated with other departments and the whole thing, and it's not just electronics or just the hardware and whatnot.
Yes.
It's computer science as well. It's all
Yeah.
one field, really.
So this project is good in futures for teach us how to cooperate with other people, right?
100%. Yep.
Okay, that's great. So that's why we set up this project. Okay, and I will say thank you, thank you, and also thank you, and faculties and student grant support of this project. So we appreciate, and you are good, very good job, and did very good job, Josh. So
Thank you.
congratulations. Okay,
Thank you.
so our and also I suppose that you give us some abandon and put all this document print out and give it to me if you want
Okay.
it. Okay, let's say
Okay.
that. Okay, again, congratulations. So you're graduate this semester, right?
Yes, sir.
Okay, okay, you're very good job. Okay,
Perfect.
thank
Thank
you. Okay, and see you on the graduation.
you.
Okay,
Yeah,
okay,
no kidding.
okay. Thank you. Okay, bye bye.
Bye.